Okay, welcome to this short introductory presentation for Workshop 2 on our Quantitative Research Methods content. What I'm going to do briefly in this presentation is just provide you with some theoretical background for the practical skills that you'll be learning in Workshop 2 and then subsequently applying again in Workshops 3 and 4. And the purpose of this presentation is to talk about, well, how do you know if the data that you've got is normally distributed? What does that actually mean in practice? And then why is that actually important in quantitative statistics? So this workshop is kind of a bridge in between Workshop 1, where we looked at Excel skills, and then Workshops 3 and 4, where we're going to be looking at some inferential statistical tests using the software package SPSS. So if you just think back to the lecture we had this week, we talked a little bit about probability, and we talked a little bit about inferential statistics, and why we use inferential statistics in null hypothesis statistical testing. So in Workshops 3 and 4, we're going to be introducing you to some very basic inferential statistical tests. But before we can do that, there's a couple of key steps that we have to go through in order to know which statistical tests we're allowed to apply. And that key step is checking whether our data is normally distributed or not, so that we can choose the correct test to apply. So, of course, in order to answer many research questions that we might ask in sport and exercise science, then we take quantitative measurements of variables that we can then objectively compare. So we might be interested as a sports scientist in measuring muscle mass or blood pressure. We might be interested in cardiorespiratory fitness or VO2 max. We might be interested in body composition, body fat percentage, etc., etc. And a key characteristic of many of the variables that we measure in sport and exercise science is that they will be normally distributed. They will come from a normal distribution. So what does that actually mean? We covered this a little bit in lecture 1, but we're just going to refresh now again in case you need a little bit of a refresher on that. What it means is that if we plot a histogram of the distribution of our data, then we'll get a histogram curve that looks like this. It has a characteristic bell shape to it. So what does this histogram actually represent? Well, on the x-axis here, what we plot is the variable that we are measuring. Okay. Now, in this case, what we're measuring is just very simple measure of body mass, okay? So we plot all the potential values from our population that we've measured of body mass, okay? And on the y-axis here, what we're looking at is the frequency of which that particular measurement occurs in our population, okay? And what you can see from that is that around measurements of 80 kilograms, just as an example in this case, that's the most common frequency occurring in our population. Yes, you can see that. And then, of course, as we get further and further away from that average value or most common value, then it becomes less and less likely as we get to these extreme values, either above or below our more average values, that we're going to observe that in our population. So the probability gets smaller and smaller the further away we go from the mean of our population here. Yes? So we get this typical curve looking like this for a lot of the variables that we will measure in sport and exercise science. Now, why is this particularly important when it comes to statistics? Why is it important that we know whether the data that we're looking at is normally distributed? And the answer is that it has this bell-shaped curve, or this normal distribution curve, has some very useful mathematical properties. And the most important one to be aware of for you guys is this concept of symmetry within this bell-shaped curve. Okay, so if I just flick forward here, so again, we're just looking at that normal bell-shaped curve. It doesn't matter which variable we're talking about here. Okay, we're just looking at a normal distribution curve. Now, in a normal distribution, what we're going to find is that our measures, our most common measures of central tendency, which are obviously the mean, which is just the average. Yes, you take all the scores in your sample or your population and you divide by the number of values that you have, and that gives you your mean. You have your median. So if we arrange all of our scores in order, then the middle value will be the median. And then we have the mode, the most common value that we measure in our population. And in a normal distribution curve, like we've got here, the most common value in our normal distribution, our mean, our median, and our mode, are all going to be equal. They're all going to be at the same value in a normal distribution curve. And that's important for a number of reasons, but we'll come back to that in just a second. The other important side of it is, of course, the variance around that mean. Okay? Remember, we talked about variance a little bit in lecture 1. So we can segment this curve up into standard deviations away from our mean value for that population. So remember, our mean is our most common or central tendency value. But then we need to know, well, how spread out are our data around that mean? So we can segment this curve up into standard deviations, which is the most common measure that we would use of our spread of our data. And we can segment up the curve, and because of this normal distribution property of the data, we know how much as a percentage of values we would expect to occur within 1 standard deviation above or below the mean, 2 standard deviations above or below the mean, 3 standard deviations above or below the mean, etc., etc. So very simply, if our data is normally distributed, like it is here in this case, then we know that 50% of our values that we would measure are going to be higher than the mean, and conversely we know that 50% of the values that we measure are going to be below the mean. Okay? Simple symmetrical mathematics. Similarly, we know that if we chunk up the data into standard deviations, so 1 standard deviation above the mean or 1 standard deviation below the mean, we know that 34% approximately of our values will fall above 1 standard deviation above the mean and 1 standard deviation below the mean. So 68% of all of our data that we measure are going to be 1 standard deviation above or below our mean value. Yes? We also know that 95% of all the values that we would measure in our population are going to be 2 standard deviations above or below our mean value. And then we can also calculate for 3 standard deviations above and below, and we know that about 99.9% of the values that we measure are going to be 3 standard deviations away from the mean. So the most important property about this normal distribution curve from the purpose of statistics is this aspect of symmetry, because that allows us to make a number of assumptions that we can employ in the statistical tests that we use. And you don't need to know about how that data is used, but you just need to know that if our data is normally distributed, we can perform a certain set of statistical tests, whereas if it's not normally distributed, so it doesn't follow this classic bell-shaped curve, then we can't make as many assumptions about the data, and therefore we have to perform a different set of statistical tests. Now, in quantitative statistics, inferential statistics, we're going to be interested in knowing whether there are differences between populations that we might be interested in. Yes, so the example I've given here is, imagine we're measuring body mass in an intervention of weight loss. Okay, so imagine this red line here is our data for pre-diet. Okay, so we've measured in a sample or a population all our body masses for each individual participant before a dietary intervention, and this is what the data looks like. Okay, and then what we're going to do is we're going to put them through a 6-month diet intervention, hoping to achieve some weight loss. If our diet is successful, what we're expecting to see is a shift in the mean of the body mass for our 2 samples that we're comparing. So we're expecting the mean of body mass for our sample here, pre-diet, to shift down the way. Yes, because we're expecting participants to lose weight. So when we calculate the average weight pre and post, we'd expect it to shift down the way. We'd also expect that our participants that fall on the extreme ends of the curve are also going to shift down as well. Yes, if the intervention is effective for everyone, then the whole of this normal distribution curve pre-diet is going to shift down the way post-diet. Okay, so when we're looking to test differences, that's what we're actually looking for. We're looking for a shift in this normal distribution curve. Now just note that that doesn't mean that every participant that we included here after the diet is going to be have lost more or be of lower body mass than everyone pre-diet, because we're comparing each individual participant pre and post. Okay, so it doesn't mean that everyone post the diet is going to be lighter than everyone pre the diet. So, just to recap on what we did in lecture 2, we talked about inferential statistics. So we use inferential statistical tests to compare the means and the variances of 2 or more samples. In this particular module, we're only interested in 2 samples. But we're comparing the means, that is the mean here, and the variances, that is our variance around the mean, between our 2 samples. In the example on the previous slide, we're talking about pre and post diet. And when we perform a statistical test, what we're doing is calculating the probability of finding a similar or a larger difference if the null hypothesis is true. And remember, the null hypothesis states that there is no difference between the populations or the samples that we're measuring. So in the case of the example I've given you on the previous slide, our hypothesis would be that the diet does not result in significant weight loss. Now remember, we calculate the probability, or p, and we have this arbitrary threshold that we use called alpha, and if p falls below this threshold of 0.05, we conclude that the probability of finding a similar or a larger difference is low enough to reject the null hypothesis. So we're confident that it's so unlikely that the difference that we have observed would be that large if there was actually no difference, that we can conclude that there probably is a difference between the 2 populations. In other words, we say if p is lower than 0.05, that there is a significant difference between our 2 samples or our 2 populations. Remember, a population is the whole, is what we're trying to make an inference about. The sample is what we're going to include in our experiment, because we can't include everyone in the population that we might be interested in. On the other hand, if we calculate our probability using our statistical test, and we find that p is greater than 0.05, then we conclude that the probability of finding a similar or larger difference is too high to be able to reject the null hypothesis. As in, the chance that we would have found a difference that large is too high to say that there is no difference between the populations. So we conclude that there is no significant difference if P falls above this 0.05 threshold. So that being the case then, why do we need to know if our data are normally distributed when we're choosing which statistical tests we can perform? And the answer is, and we're going to go up through this a little bit more in lecture 3, is that there are different types of statistical tests, we call them parametric and non-parametric tests, that we can apply depending on the characteristics of our data. And there are 3 different characteristics that we have to be interested in order to decide whether we can use a parametric test or a non-parametric test. The first of these is the scale of our data. So remember in lecture 1 we talked about different data scales and the definitions of those. So we have to know which type of data we're looking at. We have to know the distribution of our data. Is it normally distributed? That's really important. Remember, this normal distribution have a number of mathematical properties resulting from that symmetrical distribution that means we can use more powerful statistical tests on the data that we've collected because we can make more assumptions about that data. So we have to know whether it's normally distributed to know whether we can use parametric or non-parametric statistical tests. And finally, we need to know whether there are similar variances in the samples that you want to compare. But we're not going to worry too much about that at this stage. We're more interested here in knowing what scale of data we have and what distribution of data we have. Is it normally distributed or is it not normally distributed? And of course, whilst we might be able to say in theory that many of the quantitative variables we would measure in sports science will be normally distributed across the whole population, of course when we carry out studies or experiments in sport exercise science, we're often dealing with samples, or we will always be dealing with samples, and we might have a case where we have fairly small sample sizes. And remember from lecture 1 we talked about the fact that the larger the sample size we have, the more likely it is that our data is going to be representative of that whole population. And in this case, if we have small sample sizes, it might be that the sample we're dealing with is not normally distributed, just by random chance, even though the whole population is. So we always have to test the data that we've collected for our sample to check whether it's normally distributed or not. Okay, so how do we go about testing if our data is normally distributed? And that's what we're going to do in workshop 2. So we're going to use a statistical software package called SPSS. And there's a number of different things that we can do using that particular software. The first thing that we can do is we can build histograms. So we can build diagrams like I've shown you on the previous slides so that we can visually check the distribution of our data. So we can look at the data built in a histogram and we can look and see, okay, well, does that look like it's normally distributed or does it not look like it's normally distributed? So that should always be our first check. But of course, that can be quite subjective. Okay, it might look like the data is tending towards a normal distribution, but actually we probably need some kind of more objective test of whether it is or not. And there are a number of different tests that we can use to do that. So we can perform an objective statistical test of the hypothesis that our data is not normally distributed. The most common one, and the one that we're going to go through in workshop 2, is called the Shapiro-Wilks test. And that's probably the most appropriate one that you would apply in sport exercise science. But there are others out there, but you can look up those in your own time if you're interested. The Shapiro-Wilks test is the one that I would recommend that you're applying in the majority of cases. Now, just as in the situation where we might be comparing two samples, we have to have a null hypothesis for this particular test. And the null hypothesis of this test is that the sample of data that we are looking at is normally distributed. Okay, so we're testing the hypothesis that our data is not normally distributed, and that means that the null hypothesis states that the sample is normally distributed. And what we do when we apply this Shapiro-Wilks test to our data is, just like we talked about in lecture 2, is we're going to calculate the probability that the distribution of our data deviates substantially from what we would expect to see if it was normally distributed. Okay. So, just again, like we said in lecture 2, if we calculate the probability and it's lower than 0.05, then we can accept our hypothesis. We can state that p lower than 0.05, therefore our data is not normally distributed. On the other hand, if p is greater than 0.05 from the statistical test that we apply, then our data does not deviate substantially from a normal distribution. Now, so how are we going to do this? So, what I've given you in workshop 2 is similar to last week. I've given you a set of data. Now, this data has come from the workshop that you did with Nick Owen in Biomechanics 1. So you've got in that data set 4 different variables. You've got your 20-meter sprint with arms and without arms, and you've got vertical jumps with and without arms. And in workshops 3 and 4, we're going to be looking at differences between those two tests with and without arms. And we're going to be looking at correlations, relationships between performance in the sprint test and the vertical jump test. So we're going to be looking at real data that you guys have collected in class. But before we can decide which particular test that we're going to use, then we have to obviously check whether it's normally distributed. So that's what you're going to be doing in this particular workshop. You have to go through this step in order to be able to carry out the work for workshops 3 and 4. So how is it going to work? Well, I've provided you again with the set of data. I've provided you with a task list, so read through that very, very carefully. And then I provided you with a number of additional videos showing you how to open data in SPSS, how to organize data using SPSS, and then how to perform the statistical tests of normality and how to build histograms of your data as well. So you can check whether your data is normally distributed. And then what I'm asking you to do is in Microsoft Word, build a table that presents the means and the standard deviations of each of your variables. And then I want a separate column where you indicate for each variable whether or not it's normally distributed. Okay? So what you have to do in workshop 2 is work through the task list using the self-help videos that are there, and there will be myself and there will be a number of demonstrators walking around. So if you get stuck during that hour, then you can obviously ask us for questions. It's unlikely that you'll get all of the work done in the hour, so the onus will be on you ahead of workshop 3 to complete the task, and then just like last week, there'll be a model answer available for you provided at workshop 3. Okay, that's it for now. We'll see you in the workshop.